Alright, welcome to Success class on Chem 131. So today we want to look at chemical kinetics, and we'll start by defining chemical kinetics. Now chemical kinetics, please write down. Chemical kinetics is the study. Chemical kinetics is the study of the rate of chemical reaction. Chemical kinetics is the study of rates of chemical reaction. Chemical kinetics is the study of the rates of chemical reactions. So when looking at studying the rate of chemical reactions, just know you're dealing with chemical kinetics. Why do we study the rate of chemical reactions? Now, the next thing we need to look at now is rate of chemical reactions. Rate of what? What is so important about rate of chemical reactions that we study it during chemical kinetics? Now, right, the rate of chemical reactions is a measure of the speed at which a reaction is proceeding. It's a measure of the speed at which a reaction is proceeding. It's a measure of the speed at which a reaction, a reaction is proceeding. Rate of chemical reaction is a measure of the speed at which a reaction is proceeding. It's a measure of the speed at which a reaction is what? Proceeding. That is the rate, that is how fast or slow a chemical reaction is occurring. That is how fast or slow a chemical reaction is occurring. That is how fast or slow a chemical reaction is occurring. I said the rate of chemical reaction is what? Is the measure of the speed at which a reaction is proceeding. That's what I started with, right? It's the measure of the speed at which a reaction is proceeding. That is how fast or slow a chemical reaction is what? Occurring. Class, there are factors that will determine how fast or slow a chemical reaction will proceed. Class, you can take two similar size of pots. Let's use cooking as an analogy. Put 4 cups of rice in this pot, and you put 5 cups of rice in the other pots. So let this, and then light them on 2 separate source of heat. Class, first of all, one pot already has 4 cups of rice. The other pot has 5 cups of rice. That's already one factor that will determine which one we get done first. Second factor, the source of heat from this pot of rice and the source of heat from this pot of rice, are they the same? If this one has a higher temperature than this one, I think your guess is as good as mine. Which one will get ready first, right? The higher the temperature, the faster the food will get ready. So there are factors that, just like we use the analogy, there are also factors that affect how fast the reaction will proceed to give products. And we need to understand those factors. So after looking at rate of chemical reaction, which is the speed at which a reaction is occurring, or is proceeding, or the measure of how fast or slow a reaction is proceeding, before I give you those factors, I'd like to go further to give you the mathematical definition, because this is the theoretical definition. So if you are asked to calculate how fast or slow a reaction is proceeding, mathematically, the rate of chemical reaction, R, is the ratio of the change in concentration. Change in what? Concentration of product or reactant. Product or what? Change in concentration of product or reactant divided by change in time. Change in what? Time. So if you want to check how fast a reaction is occurring, we're going to check its initial concentration and its final concentration. Has there been a major change? And now how short a time, or how fast a time did that change occur? Will now tell us how fast the reaction is proceeding. Class, if we have a reaction A plus B to give C, if we have a reaction A plus B to give C, obviously we all know by now that the left-hand side of the reaction represents the reactant side, and the right-hand side of the reaction represents the product side. Class, before the reaction started, we take account of the initial concentration of the reactant. Let us say that this reactant has an initial concentration of 0.5 m. And when I mean m, I believe we know that it means mole per liter or mole per dm3. A reactant having a concentration of 0.5 m, but after before the reaction started, the time is 0 seconds. So this is the initial concentration. Let's call this C1. And let's call the initial time T1. So the reaction has not started yet. So it's T 0 seconds. The initial concentration is 0.5 m. Class, the reaction then proceeds, and after a time interval of 10 seconds, we observe that the concentration has reduced. So the final concentration, we now observe that is 0.3 m. Class, this is reaction 1. Let's assume a similar reaction that is also carried out. And again, we started with 0.5 m. Time interval, initial time is 0 seconds. Before the reaction takes place, there's no time spent yet now, so 0. Similar reaction, but this time around, we find out that the final concentration is 0.4 m. In the same time interval of 10 seconds. After 10. So class, looking at the change in concentration in similar time interval, which will you say reacted faster? Which of these models will you say is the reaction occurring what faster? Is it A or is it B? Because in 10 seconds, the reaction moved from 0.5 to 0.4. Someone is saying B. Well done. And in the same 10 seconds, the reaction moved from 0.5 to 0.3. In which of these cases is the reaction occurring faster? Because I said the word done for B, I didn't mean you are wrong. Then A, you don't condemn B and A now. Just leave it like that. Class, is it A or B? Have a mind of your own, just think. If you still have B, that's in your mind, say it. B, right? Class, if the reactant has moved from 0.5 to 0.4, only, what's the change between 0.5 and 0.4? Only 0.1 m of A has decomposed or has been consumed. But class, in this other case, already 0.5 minus 0.3. There's a difference of 0.2 already consumed. Class, I think the first one is the one that has a faster reaction. Because class, in terms of the reactants, when we're checking how fast the reaction is proceeding, from the reactant point of view, we look at how fast is the reactant consumed, how fast is the reactant used up. Because class, I must explain something to you here now. Follow me carefully, follow me carefully. The class, in a reaction, A plus B to give C. There are two things that are happening simultaneously in every reaction. There are two things happening simultaneously in every reaction. As soon as the reaction starts, two things are happening simultaneously. One is on the left-hand side, and the other is on the right-hand. Class, on the left-hand side, there is what we call decomposition. Decomposition. Because class, for C to be formed, A and B must be consumed. A and B must be used up. For this product C to be formed, so there's formation of product on the right hand side, but there's decomposition on the left hand side. Class, I like to explain that there's a loss on the left hand side and there's a gain on the right hand. Class, for there to be a gain on the right hand side, there must be a loss on the left hand side. Class, if you go to the market and you buy all your ingredients, you want to cook soup. If soup is ready and none of the ingredients has reduced, have you cooked? You should not use up any of the ingredients, but soup is ready. Second chop, may I make Gary out? Say, how? meat still dey ground. Say, no worry, just leave am. It doesn't make sense, right?
Yeah.
Those watching online, sorry for the pigeon. Now, so for the product to be formed, the reactant have to undergo a decomposition. They must mix up so that we can form C. A and B came together to work and consume to form C. So class, for the product to be formed, the reactant must be used up. So when we want to check how fast the reaction is proceeding from the reactant side, we're going to check how fast is the reactant going down, how fast has it reduced. Now looking at this, A has reduced from 0.5 to 0.3 in the same 10 seconds. But this B reduced from 0.5 to 0.4. This guy is reducing faster than this. Right? Meaning that this guy has a higher rate of. But class, when you go to the product side, this guy has higher rate. Because in the product side, we check, we don't look at how fast it's decomposed, how fast is it formation. So we look at how fast, how much gain is on the right hand. On the right hand side, we look at rate of what? Formation. So if you want to define rate of chemical reaction, please write that the rate of chemical reaction can be defined in two ways. One from the reactant side and two from the product side. Rate of chemical reaction can be defined in two ways. One from the reactant side, two from the product side. Rate of the chemical reaction can be defined in two ways. One from the reactant side, two from the what? Product side. Rate of chemical reaction can be defined in two ways. One from the reactant side, two from the product side. Rate of chemical reaction can be defined in two ways. One from the reactant side, two from the product side. Plus, now let's start with one from the reactants. From the reactant, rate of chemical reaction can be defined as rate of decomposition or rate of consumption. Rate of decomposition, rate of consumption, rate of disappearance. All these words can be used for reactant. Rate of decomposition, rate of consumption, rate of disappearance. From the left-hand side, rate of chemical reaction can be defined as rate of decomposition, rate of consumption, rate of disappearance. Rate of decomposition, rate of consumption, rate of what? Disappearance. Class. Just like I said earlier, your ingredients must disappear so that your soup can appear. The ingredients you bought from the market to make soup, they must disappear. If not all, at least most or some of them. Because of course, after the reaction is over, some of it's not all reactants that are used up, right? The reactants that are still remaining after the reaction is over are called excess reagents. Are called what?
Excess reagents.
Those reactants that are still remaining after the reaction is over. So it's normal. You can go to market, but it's not all the fish you used. But that one is funny, but which one don't you use most of the time? Let's say crayfish. No. Yes, talk to us. Which one don't you use? Pepper, right? Correct. Salt, maybe spices, the curry. You say this next curry I used to make next meal. Or you understand, you bought in rice for 1 week. You won't eat everything today now. So the reagents that have not yet been reacted are called excess reagent. Why the reagent that finishes first is the limiting reagent. Now class, follow me. So on the reactant side we have decomposition, consumption, disappearance. On the product side we have formation, we have appearance. So from the product side you can define rate of reaction as rate of formation, rate of appearance. Rate of formation, rate of appearance. Rate of formation, rate of what? Appearance. From the product side, rate of formation, rate of what? Appearance. Rate of formation, rate of appearance. Class. So class, the rate of chemical reaction, if you have A plus B to give C, and we say rate of chemical reaction is change in concentration, right? Change in what? If I don't want to write change, I can put delta, I can put what? If I don't want to write concentration, I can put this bracket. This bracket stands for concentration in Chem 131. This bracket stands for concentration. So rate of chemical reaction can be delta means change. This bracket concern of A all over change in time. Rate of chemical reaction can be change in concentration of B all over change in, and rate of chemical reaction can be equal to rate change in concentration of C all over changing. Don't forget, the rate of chemical reaction is change in concentration all over change in time. Remember that? Change in concentration from C2 to C1 all over change in time. Class, but there's one more thing. Remember I told you that there's a loss. There must be a loss here for there to be a gain here. So class, usually attach a negative sign to the, if you calculate the rate of the reaction from the reactant side, attach a negative sign to show the what, the loss. But if you calculate the rate of reaction from the product side, attach a positive to show the gain. So on the left hand side is a loss, on the left hand side is a gain. So if you are calculating the rate of reaction from the reactant side, attach a negative showing disappearance, showing loss, showing decomposition. So there's a loss here. But if you are calculating the rate of reaction on the product side, attach a positive sign. So if you have to implement that, means that change in A is reactant, right? Minus. Change in B is also minus. But C is product, plus, right? Yes. Oh, I think nice building the foundation in here step by step. Class. Moving forward. Any of this could be used to calculate the rate of the chemical reaction. Change in A all over time, change in B all over time, change in C all over. Class. Let me tell you something. So this A now, we can call this RA, we can call this RB, we can call this R. Follow me. What will we say is RA? RA, because A is a reactant, RA must be rate of disappearance of A, or rate of decomposition of A, or rate of consumption of A. Class. RA means rate of disappearance of A. RB means rate of disappearance of B. RC means rate of formation of C. But class, we still have what we call normal R that does not carry A, B, or C. That is overall rate of the chemical reaction. Overall what? Rate of the chemical reaction. Now class, looking at this reaction, we have 1A plus 1B to give 1C. Each of the components of the reaction have the same number of moles. Class, for this type of reaction, when all the components of the reaction have the same number of moles, then we can see that the overall rate of the chemical reaction can be equal to RA, also equals to RB, equals to RC. Look at new marker. Even old marker is clearer than this. New marker. So class, the overall rate of the chemical reaction equals to RA, equals to RB, equals to RC. If all the components of the reaction have the same number of moles. So class, if that's to find the overall rate of this chemical reaction, and you get RA, you've gotten the overall rate. Or you get RB, you've gotten the overall. If you get RC, you've also gotten the overall rate. This only applies if all the components of the reaction have the same number of what? Moles. But whenever you're giving a reaction where they don't have the same number of moles, class, something else will come in. Follow me now. If you have 2A plus 3B to give 4C. Class, this is no longer true that R equals to RA equals to RB equals to RC. We must factor in the words, their stoichiometric coefficients. The stoichiometric coefficient of each component of the reaction must be factored into the formula now. So R cannot just be equal to RA, RB equals to RC. Why? Because each component of the reaction has different number of moles. Class, the overall rate of the chemical reaction, if you have to look for the overall rate of the chemical reaction, is going to be RA divided by the stoichiometric coefficient of A in the reaction 2. Or RB divided by the stoichiometric coefficient of B in the reaction. Or RC divided by the what? Stoichiometric coefficient of the reaction, C in the reaction. Class, this is what now applies when they have different number of what? Moles. Class, are we together? So when they are, it's just A, B to give C, and they have the same number of moles. No problem. The rate of chemical reaction is equals to Ra, equals to Rb, equals to R. Don't divide by anything because they don't even have anything to divide by. But as soon as the number of moles are different for each component, then you cannot just say that the rate of reaction is Ra, class, you'll be wrong. You do not consider that A is occurring how many times? Twice. B is occurring how many times? And C is 4 number of moles. You must factor that in when calculating your rate of chemical reaction. Class, is that clear? Very, very important. Write down factors affecting rate of chemical reaction. Factors affecting rate of chemical reaction. Once we finish factors, we'll start taking questions and calculation. Examples on how to use these formulas. Factors affecting rate of chemical reaction. 1. Temperature. Factors affecting rate of chemical reaction. 1. What? Temperatures. Factors affecting rate of chemical reaction. 1 is what? Temperature. Note. The higher the temperature, the faster the chemical reaction will proceed. Hence, the higher the rate of the chemical reactions. Please. Can't do anything serious in this country. Don't be teaching some of this. Class. The higher the temperature, the faster the chemical reaction will proceed. Hence, the higher the rate of the chemical reaction. The higher the temperature, the faster the chemical reaction will proceed. Hence, the faster the rate of the chemical reaction. The higher the rate of the chemical reaction, sorry. The higher the temperature, the faster the chemical reaction will do what? Proceed. Hence, the higher the rate of the chemical reaction. So, higher temperatures will lead to the reaction occurring faster, right? And if the reaction occurs faster, it has increased the rate of the chemical reaction. Because rate of reaction is how fast or slow the chemical reaction is occurring, right? So if it is fast, rate of reaction will increase. If it is slow, rate of reaction will reduce. Are you following me? This is how what temperature affects the rate of chemical reaction. Why? Why is it that when the temperature is increased, the reaction occurs faster? Because class, when temperature is increased, the rate of collision between the molecules increases. The rate of collision between the molecules of the reactant does what? Class. A and B wants to form C. What usually happens in the reaction is that the molecules of A collide with the molecules of B. Class, the more the molecules of A and the molecules of B are colliding in class, the higher the chances of C form because class. To be honest, when A and B react, what happens is that not all the molecules of A and B that collide will lead to formation of C. This is what we call effective collisions. This is what we call effective. So what happens when A and B wants to react, the molecules of A and molecules of B collide. Class, some of them will collide and bounce back. C will not be formed. Many times the molecules of A and B collide and bounce, and C is not. But class, sometimes when they bounce and they collide and C is formed, that kind of collision is referred to as what? Effective collision. So in case you ask in the exam, collision that leads to formation of product is known as that, effective. Because this course is also 35 subjective. This course is also what? 35 subjective. This same pattern with Chem 132, which is organic. We are expecting 35 subjective questions. So class, how does the increase in temperature help effective collision, class? If you increase the temperature, the collision frequency is increased. This is what we call collision frequency. Collision frequency is the amount of time two molecules collide. How frequent do two molecules collide? Collision what? Frequency. Plus, if A and B collide 100 times and A and B collide 1,000 times, where do you have more chance of C form? Is it not 1,000? You give someone 2 chances, you give someone 10 chances. Who has more chance of success? 10. Because he has a chance to try 10 times. The other person also has a chance to try what? So there are more chances. So what temperature does is that it's hastening up the collision. Collision occurs faster because when you increase temperature, you increase entropy, increase in disorderliness of the system. And when you increase that, the molecules react faster. And when the molecules react faster, there's higher chance of effective collision occurring. And the more effective collision occurs, the more C is formed. And the more C is formed, the more the rate of chemical reaction. Are we together, class? 2, let's look at concentration. The next factor that affects rate of chemical reaction. Concentration. Are we together? Note, when the concentration of a species is increased, there will be increase in number of particles per unit area. When the concentration of the species is increased, there will be increase in number of particles per unit area. When the concentration of the species is what? Increased. When the concentration of the species is increased, there will be increase in number of particles per unit area. There will be increase in number of particles per unit area. There will be increase in number of particles per unit what? Area. Which will result in more collisions. Which will result in more collisions among the reactant particles. Which will result in more collisions among the reactant particles. Which will result in more what? Collision among the reactant particles. And everybody now knows that when there's increase in collision, you know what that means, Abi? We understand now. Which results in what? More collision among the reactant particles. And the increase in collision will lead to what? Increase in the rate of the chemical reaction. And increase in collision will lead to increase in the rate of chemical reaction. Class. So if A and B react and A and B are concentrated, and another A and B react, but this time A and B are dilute. They are not. No, the opposite of concentration is dilute, right? The opposite of concentration is what? When two concentrated A and B react, and when two dilute A and B react, expect concentrated A and B to what? To have higher rate of chemical reaction, to react faster, to react. The rate of reaction in this first one will be higher than the rate of reaction in the second one. Let's go to the third factor, physical state of the reacting species. Physical state of the what? Yeah. Reacting species. Physical state. This one is very easy to explain. Physical state of the reacting species class. This particular factor is the reason why when we are cooking, we what? We turn our Maggi cube into powder, right? From lump to and spread it, right? By spreading it out, you're increasing the surface, and then the Maggi cube can have more effective collision. Class, you don't just throw your Maggi cube inside the soup like that. So, reactants, physical state, how the reactants appear can also affect if the reaction will occur faster or slower. Reactants in powder form are known to what? React faster than reactants in long form. If the reactants are in long form, before they start reacting, they will first want to first break down, right? The time it takes to break down, someone that's in powder form has already react. That makes sense? So if you understand already, anything you're writing in your book now, you're just writing because it will not be as if you did not write. But understanding is the most important thing. Class. If everything we are taught can stay in our brain, you know we don't need to write. Class, why are we writing? If everything you are taught can stay in your brain, do you need to write anything? Class, it's because we are not confident that everything we are hearing we will remember it. That's why we are writing. So to go back to so as much as possible, if you can understand, but still write too. Writing backs up what you understand. Physical state of reacting species. Note, when solid reactants are grounded to powdered form, the reaction tends to proceed more rapidly. Note, when solid reactants are grounded to powdered form, the reaction tends to proceed more rapidly. This explains how the change in physical states of species would affect rate of chemical reaction. This explains how the change in physical state of the species would affect what rate of chemical reaction. This explains how what change in physical state of the species could affect rate of chemical reaction. This explains how what change in physical state of the species could affect rate of chemical. This explains how what the change in physical state of the what species could affect rate of chemical. 4 is catalyst. How will catalyst affect rate of chemical reaction? How will what? Catalyst affect rate of chemical reaction. A catalyst right now is a substance that can increase rate of a chemical reaction without being consumed. A catalyst is a substance that can increase rate of chemical reaction without being consumed. A catalyst is a substance that can increase. See, they ask you in the exam. Dash is a substance that can increase rate of chemical reaction without being consumed. Catalyst is the answer. A catalyst is a substance that can do what? Increase rate of chemical reaction without being what? Consumed. Note. When a catalyst is added to a reaction, the activation energy needed for the reaction to proceed. Note, when a catalyst is added to a reaction, the activation energy needed for a reaction to proceed from reactant to product is reduced. When a catalyst is added to a reaction, the activation energy needed for a reaction to proceed from reactant to what? Product is what? Is reduced. Class. When a catalyst is what? Added to a reaction, the activation energy needed, what? Needed for a reaction to proceed from reactant to what? Product is what? Is reduced. Class. Activation energy is just like cutoff mark. Cutoff mark of the reaction. Class. Every reaction has its cutoff mark, its activation energy. Class. If the energy, minimum amount of energy is not attained, the reaction cannot proceed to products. So let's say a reaction needs 5,000 joules before anything can happen. 5,000 joules is needed. What the catalyst does is that it reduces the requirement from 5,000 to 3,000 joules. Class, this reaction will now occur faster. Because class, someone that does not have a catalyst is still looking for 5,000. You that has catalyst, you are just looking for 3,000. So who has a higher chance of success? 3,000, right? Because you have a lesser target to meet. No, we have two types. Some students just say, just give me C, I'm okay. Just give me C, why some say I want A? Those two will not read the same way. The way someone that is looking for C will read is different from the way someone that is reading for A will. But the funny thing about this thing is that someone that is looking for C should not read for C. You should be reading for A. So even if you drop, you go to, because class, one thing in life is that prepare for failure as well. How do you prepare for failure? Target higher than your target so that even if you fail, failure is relative. Someone that is looking for 100 and he got 70, he failed though. Because your target, once you didn't meet your target, you actually fail. Failure is inability to meet expectation of what was expected, a target. Target 100, you failed to 70, you failed, but your failure landed you in success. But someone that says, I won't see, just give me 50, I don't like stress, I beg. This is first semester, my head is hot, I beg. I don't want to hear anything. Just give me what? If 100 fell to 70, that's 30 difference. When 50 is falling, how far? Sweet 20 or sweet 16. Sweet 4 to sweet 16 and then. Because some people, there are students in this school, when your food is up and your parents ask to send, you send fake results to their parents. It happens every year. I don't want college like that. When it's up on that, you send your results to Daddy, I'm coming. Let me cook. The guy wants to cook. You now start planning results. The one that you lost C, form it around. Now class. So catalyst reduces the activation energy required for a reaction to proceed from reactant to what? Product. And if it does that, it will help the reaction occur faster. It will help the reaction to occur faster. Good. Let's take this question down now. We have looked at the 4 factors that affect rate of chemical. It was observed during the decomposition reaction of ammonia. It was observed during the decomposition reaction of ammonia. It was observed during the decomposition reaction of ammonia. It was what? Observed during the decomposition reaction of ammonia. It was observed during the decomposition reaction of ammonia that hydrogen was being formed. It was observed during the decomposition reaction of ammonia. It was observed during the decomposition reaction of ammonia that hydrogen was being formed. Hydrogen was being formed at the rate of 0.062. At the rate of 0.062 mole per liter per. It was observed during the decomposition reaction of ammonia that hydrogen was being formed at the rate of 0.062 mole per liter per. According to the following reaction, 2NH3 to give N2 plus 3H2. 2NH3 to give what? N2 plus 3H2. 2NH3 to give N2 plus 3H2. NH3 to give what? N2 plus 3H. Calculate the following. Calculate the 1. Rate of decomposition of NH3. 1. Rate of decomposition of what? 2. Rate of formation of N2. 2. Rate of formation of N2. 3. Rate of the chemical reaction. Rate of the chemical class. I remember when I was telling you that you can get RA, RB, RC, and there's still what they call overall rate of the chemical R, right? So that's what they're saying, rate of the chemical class. Note when they asked you to NA3, what word did they use for NA3? Rate of decomposition. When they came to N2, what word did they use? Rate of formation. So even your question, your examiner is using the right words. I told you that in the reactor side, the words we use: decomposition, disappearance, consume. But on the product side, we use appearance, formation, production. Formation, appearance. Product is formation, appearance. Reactant is disappearance, decomposition. So know that they use different words for this and this. So we have to find 3 things here, class. But they only gave us 1. Class, on the reaction, they told us that it was observed during the decomposition reaction of ammonia that hydrogen was being formed at the rate of this, right? So this is rate of formation of hydro. No wonder they didn't ask us to find the rate of formation of hydrogen because they gave it to us already, right? Hydrogen was being formed at the rate of 0.062 mole per liter per seconds. Find the rate of decomposition of ammonia, find rate of formation of nitrogen, and find the overall rate of the chemical reaction. Class, based on what I taught you, looking at the stoichiometric coefficient, this is 2, this is 1, this is 3. The overall rate of the chemical reaction must be equal to RNH3 divided by what? 2. Must be equal to Rn2 divided by what? 1, because it is 1, right? Because to RH2 divided by what? 3. Class, you get? Where does this R represent the overall rate of the chemical reaction? Which is this third one they asked us, find the rate of the chemical reaction. Among everybody here, we only have one person, RH2. RH2, the total hydrogen was being from hydrogen was being at the rate of 0.062. So we have RH2. Class, let us box this first 2 parts of the equation. From RH2, I can get Rn2 easily. So from this part of the equation, we have the Rn2 all over 1, right? Equals to RH2 divided by Rn2 over 1 is Rn2, right? Rn2 is 0.06. Now divided by what? 0.062 divided by 3 is 0.02 mole per liter per second. Class, I've just gotten the rate of formation of nitrogen. Rate of what? I've answered one of the questions. 0.021 mole per liter per second. 0.021 mole per liter per. If I have Rn2, I can clean this box and box in this total. Box in this. Because every part of this equation is correct, but this equals to this I can box in N2 and use to solve. This part I boxed in now says that Rn3 divided by 2 must be equal to Rn2 divided by 1, right? And I already have Rn2 here, right? I just got Rn2 now. Let's do this one up. So we have Rnh3 divided by 2 must be equal to Rn2 divided by 1. What is Rn2 divided by Rn2, right? If you cross multiply, it means that Rnh3 equals to 2 times Rn. So Rn3, follow me. So what's Rn2 class? 0.02. This is Rn2 here, right? 0.021. So what is 2 multiplied by 0.021? 0.04 mole per liter per. So my RNA3 I just got in 0.042 mole per liter per. We have to tell students. Some students are writing, some students are paying attention. Students are writing, some are paying. You shouldn't be writing if you understand what, okay, I know what you want to do. I've understood the answer. Show me, okay, just box those two. I can figure it out. Except that you can't figure it out, you shouldn't be writing what you don't understand. Exam is final answer, no explanation. No time for too much talk. The last one is rate of chemical reaction. Rate of chemical. Which two will I box to easily get R? I can box this last two, right? R equals to NH3 divided by 3. Let's do that. Okay. R equals to what? RNH3 divided by what? 2. What's RNH3? We just got it here, 0.04. Now divided by what? 0.0 what? Notice that the overall rate of the chemical reaction is similar to the rate of formation of nitrogen. Do you notice? It is the same rate of formation of nitrogen. Why? Because nitrogen is the only person that his number of moles will still remain. Remember when I told that when A plus B plus C, there is no number of moles. Rate of reaction is equal to all of them, the same thing, right? If they are 1, 1, 1, the rate of chemical reaction is the same for each of. That's why the rate of chemical reaction is the same for nitrogen. But nitrogen still remain. Class, are we following? Let's now go to rate equation. Write down rate equation. I shift. I shift a bit. Rate equation or rate law. But don't worry. You need to write understandable. Rate equation or rate law. For those don't writing, write down rate equation or rate law. Rate equation or rate law. Obviously, there are many more examples. But in a class like this, if you take all examples, we will not leave here today. So as a smart student, you will now go to the past question. Look for all possible questions on this aspect and take them to improve your own self. That's everybody can attend to, and everybody will get the same score. What you get of this tutorial, from one person will get of this tutorial. Depending on how you use what we are giving you. So you can still attend to tutorial and not do well if you don't use the information well. Go to your past exam question, screen out all questions like this there, and beef up yourself. Improve your. Don't just relax on one example. It's too simple. One example is not enough to say you are ready for the exam. Go to your past exam question. Take more questions. Class, please be fast, be fast, be fast. Next subheading, rate law. Or rate equation, rate law or rate equation, rate law or rate equation. Can I clean the board? Can I clean the board? You are still writing? Okay, pause the video, pause the video. Now class, rate law states that, the rate law states that the rate law states that the rate of a chemical reaction is proportional. Rate law states that the rate of a chemical reaction is proportional to the concentration of reactant species. The rate law states that the rate of the chemical reaction is proportional to the concentration. So if you're following us online, we are now in rate law or rate equation. Please take note. Rate law or rate equation. Rate law states that the rate of the chemical reaction is proportional to the concentration of the reactant species raised to the power of an exponent. Raised to the power of an exponent. As the rate law states that the rate of the chemical reaction, rate law states that the rate of the chemical reaction is proportional to the concentration of reactant species. It's proportional to the concentration of reactant species raised to the power of an exponent known as the order. Known as the what? Order. Raised to the power of an exponent known as the what? Order of the reaction. Known as the order of the rate law states that the rate of the chemical reaction is proportional to the concentration of the reactant species raised to the power of the what? Order of the what? Raised to the power of an exponent. The exponent is known as the what? Order. Exponent means a power. Index. And that index is the power. Is the what? Power. Class. Why do we say rate law or rate equation? Rate law is the theoretical statement. State it. Once you represent it mathematically, it becomes rate equation. It becomes what? When you are stating it theoretically, it's rate law. Once you write the mathematical implication of that, it becomes rate equation. So the equation that is used to represent the rate law is known as rate equation. The equation that expresses what the rate law is trying to say is rate equation. Is rate. So mathematically, rate equation, rate law from the rate law says that the rate of chemical reaction R is directly proportional to the concentration. What's concentration? Bracket, right? Note that I did not mention product, only reactant species. So if you have a reaction A to give B, the rate equation or the rate law states that the rate of the chemical reaction R is proportional to the concentration. This bracket stands for concentration of the reactant. A is the reactant, B is not mentioned. Then they say raise to the power of an exponent. Let the exponent be x. And this x represents order of the order. But class, let us have another reaction A plus B to give C. So this rate equation here is for an equation whereby you also have A to give B. You only have one reactant. You only have one. When you only have one reactant, when you only have one reactant. This is the rate equation for when you have one reactant. Once the reactants become two class, the rate equation considers all of the reactants. The rate equation says that the rate of chemical reaction R is proportional to the concentration of the reactant, right? So this is the first reactant. Let this one be X. Second reactant, let this one be. So the order now is what? X and. So therefore, in this kind of reaction, when you have two order, the overall order of the reaction will be summation of the X plus Y. Overall what? X plus, because we have two exponents. We have what? Why do we have two exponents? Because we now have two reactants. We now have what? When we have only one reactant, we have only one exponent, right? So we have only one order. Exponent represents the order. The exponent represents the. When we have only one reactant, we have only one order X. Once we have two reactants, we now have two order X and. So therefore, if we have to find the order of the reaction, which one? We're going to use X, we're going to use Y, we're going to use overall order. X plus what? Class, even if we have three reactants, it will be X, Y, Z. If we have three reactants, A plus B plus C to give D, our rate of the equation, rate equation will be R is proportional function of what? A raised by X, B raised by C raised by. Note that no two reactants have the same order. So that's why we use X to represent A, we use Y to represent B, we use Z to represent C. We do not use the same because we don't want to assume that they are the same. So the order for A, as we have order for B, we have order for C. So what must be the overall order now? X plus Y plus. Are we following class? Class, now that I've understood that, let's go back to this first one and push it further. My chemist. 1, 3, 1. Chemical Kinetics. Class. I believe we are finished writing this now. So class, I want to show you something. Anytime you have proportionality sign, anytime we have a proportionality sign, anytime there is a proportionality sign, a constant can come in to break that proportionality sign. So that instead of R is proportional to A raised by X, R will now be equal to K. The constant that comes in is what? K concentration of A raised to the power of what? X. Or R can be equal to K concentration of A raised to the power of X, B raised to the power of. This constant that comes in K is referred to as the rate constant. Rate. So please do not confuse rate of the chemical reaction with rate constant. The rate of chemical reaction is R, rate constant is K. Rate of chemical reaction is R, rate constant is what? K. Are we together? Without wasting more time, our next subheading should be order of reactions. Order of reactions. Order of what? Reactions. Class, we're going to be looking at zero order reactions, first order reaction, and second order reaction. We're going to be looking at zero order reaction, first order reaction, second order reaction. Zero order reaction, first order, and what? Second order. So our subheading is order of reaction. We're looking at zero order reaction. First order reaction. Second. So after writing order of reaction, can we start with zero order now? Let us start with zero order. A zero order reaction is a reaction, right now. Very important. We'll be asked in the exam actually. Please, this is not just a definition. A zero order reaction is a reaction in which the rate of reaction. A zero order reaction is a reaction in which the rate of reaction is independent. A zero order reaction is a reaction in which the rate of reaction is independent of the concentration of the reactant species. A zero order reaction is a reaction in which the rate of the reaction is independent of the concentration of the reactant species. A zero order reaction is a reaction in which the rate of the reaction is what? Independent of the concentration of the reactant species. So the rate of reaction does not depend on concentrations. And I'll explain why. A zero order reaction is a reaction in which what? The rate of the reaction is what? Independent of the what? Concentration of the reactant species. This implies that the rate of disappearance of a zero order reaction is constant. This implies that the rate of disappearance of a zero order reaction is constant. And equal to the rate constant of the reaction. And equal to the rate constant of the reaction. I'll explain, don't worry. Let's have the notes ready, I'll explain. This implies that the rate of disappearance of a zero order reaction is constant and is equal to the rate constant of the reaction. This implies that the rate of disappearance of a zero order reaction This implies that the rate of what? Disappearance of a zero order reaction is what? Is constant and equal to the rate constant. Equal to the what? Is equal to the rate constant of the reaction. Class, follow me. Note that the units of a zero order reaction are expressed as mole per liter per second. The units of the zero order reaction are expressed. This is asked in the exam. Please take note. Unit of a zero order reaction is expressed as mole per liter per seconds. Please, when you're studying your person, do not expect exact repetition. The lecturers are now aware that everybody's using past questions. They are seeing it in your halls. There was a time I used to tell students, everybody keep a question in your bag. If they are seeing all of the person in the class like this, they will know that you have studied it. They're already angry, they're already wondering how are we getting the exam questions. Okay, I remember, thank God, first semester I wrote the exam. You didn't give your question in your bag. The chair was saying before the exam that nobody will go there. One of the things I was just saying that to say past question. It happened, right? I told you, will not give your question in your bag. So how are you now having the questions there? That's what they'll be thinking. So they're already angry and all of you are not showing your passion in the class. But it's not only me that's selling, so I cannot tell everybody to tell their people that are selling to not drop passion in the bag. When I ask them, I say, don't. That's if lecturer is saying everybody to pass question. They will not set it again now. Hide your past questions. Hide your past questions. If they don't know that you know, then one lecturer can just swap and just lazily set it instead. There's no time, let me just set it there and they don't have the exam. After we collected the question from them. Why are they not repeating questions like that again? Because in recent years, they stopped repeating past questions. It still doesn't mean that person is no longer important. But if you're studying person that you just repeat it like that, you are joking. They now know. In fact, I think someone even told me that one of the lecturers said that they are not going to repeat person this year, something like that. I don't know what that was telling me. Someone messaged me on the WhatsApp. That's how I heard that the lecturer said that they will not repeat past questions this year. They know that you have it. All of you are carrying it and putting it in front. But studying person is not for you to pray that they should repeat that exact question. It's to have more exposure to exam standard examples, right? Because the examples you're giving in the test are too simple. You need tough exam standard, right? So please, not that same. When they finish exam, they don't repeat person. They will not feel that you have duped them. So it's not bringing any person. Is that why you got passion? Why did you go and shout for school and they gave the test that did not bring anything? Passion is to expose to what they said last year. It's not me that will go and tell the child to set it or not. I did not do a bad thing by giving you an exam that they wrote last. I want to confirm the validity of the passion. Go to your friend in 200 level. I tell my students, I'm sure of my own passion. Go to your friend in 200 level. Ask her. She may be you won last year. This is the exam you wrote last. So anybody can compile anything and tell you that it's an exam question. You were not here last year, you won't know. So for me, the one I'm saying, go to your friend in 200 level. Ask her, is this what you wrote last? Your own friend will not lie to you now. Right? Confirm if it's the exam or for me, I get the direct exam questions. I get the direct exam and I solve it myself so I can assist students. Some of my questions I even handwritten the hand. So I'm using those things. Don't study exam past question for repetition. Study it to expose yourself to more exam rules. Study it to know the line of thought of the lecturer. Okay, this is how they set it. Now that they will bring this thing out exactly. If some of them now repeat like that, thank God. But doesn't mean that because they don't repeat any past question, then you wasted your money or that person has failed the purpose. Does not fail the purpose. Normally you need more examples. Look at that question we took now. That first example we solved that we rate of NA3. You know that's the only example in your test, in the full test, and on that particular aspect. Is it going to be enough? No. So if you don't have passion, where will you see more examples to solve? Class, you get the point? Yes. So people should understand the essence of past question. Maybe we say that buy passion is just a marketing skill. Sometimes when I say buy passion, so if you don't say it like that, you will not buy. That they will repeat it upon the exam. If you don't say it like that, it's a marketing skill. Let me just tell you now. But I'm telling you the truth because you are my students. It's not, you're not studying it for repetition, you're studying it for your own benefit, for your words. So even if nothing comes out, don't see that you are failed, but you're able to solve well. Because of the ones you have solved before that can able to solve well. Please take. So when you're getting past this, I'll tell you, you are getting it for preparation. But if they repeat anyone, thank. I'm not saying they will never repeat, so they used to repeat. Some of you used to see it. Some of you are studying a particular year and you see that my solution I'll say is repeated. Go to the previous year. I even should write the repeated past. So they repeat actually. I want to get about anything can happen. Please take note. Now, what is a zero order reaction class? In a zero order reaction, it means that the overall order of the reaction is 0. The overall order of the reaction is what? 0. The total order of the reaction is 0. Class. So let us write the rate equation for a zero order reaction. If you have a reaction A to give B, and you have to write the rate equation for it, and it's a zero order reaction, following the information I told you about rate equation, R is proportional to concentration. What's the rate law? Rate law says that the rate of chemical reaction is directly proportional to the constant of who? Reactant. It doesn't consider the product. Remember that. Raised to the power of the what? Order X. But class, if they say this reaction is a zero order, it means that we can replace X with what? We now know the order. Class, we only use those X, Y, and Z when we don't know the order of the. But if they're giving you a reaction, they say that given that the overall order of the reaction is 1, you know that this reaction is 1. That's the first order. Given that the overall order of the reaction is 2, it's the second order. Given that the overall order of the reaction is 0, it's the 0 order. So it's not even that we put X here. If the order of the reaction is not, put the particular order 0. But remember that anything raised to power 0 is what? 1. So it means that before we even put 1, class, follow me. Let's bring in the constant first. R equals to K, right? A raised to power. R equals to K raised to power what? But A raised to power 0 is 1. A raised to power 0 is what? This A raised to power 0 being 1 does not affect K. K is not following A to carry this 0. So K is still here. So this is K times 1. K times 1 is K, right? This is where we say that the rate of disappearance equals to the rate constant K. So in a zero order reaction, the rate of chemical reaction is equal to the rate constant K. Class, it's not true for all other type of reaction, but for zero order it is true. Once you have gotten the rate constant, you have gotten the rate of the reaction. And once you've gotten the rate of the reaction, you've gotten the rate. Because they're equal to each other, they also share the same unit. Mole, which I gave you. Mole per liter per. They share the same units. There's also a point we take. I said when we started rate of zero order reaction. When I started zero order, I said it's a kind of reaction in which the rate of the reaction is independent of the concentration of the reactor. Right? Go back to your notes. It's independent of the concentration of the reactor. Independent does not depend, and actually it doesn't depend on the concentration because class, this 0 will make the concentration of this reactant A disappear, right? Meaning that R is no longer relying on concentration of the reactant, right? R is just equals to what? K. This is why we said that the zero order reaction is the reaction in which the rate of the reaction is on the concentration of the reactant. So R is just equal to K. The concentration of the reactant has gone, raised to power 0 is 1, right? Please take note. We also have what we call integrated rate equation. Integrated what? Rate equation. Integrated rate equation for a zero order reaction is 8 equals to A naught minus KT. AT equals to A naught minus what? This is called integrated rate equation. And this is one we're going to use for solving. Integrated rate equation. Integrated rate equation. Integrated what? Rate equation. Class, AT means A naught, that's how we know. A naught represents the initial concentration of the reactant. Initial what? AT represents final concentration after a particular time. Final what? K represents the rate constant. Rate. Have mercy, O Lord. Class, this formula we're going to use for solving. You could also be asked to state the integrated rate equation for a zero order reaction. It's not that long that you cannot come out as subjective because this is just one line. Write down the integrated expression for a zero order 80 equals to A naught minus 80. A means any, what we're using A is that depending on the reactant, right? A stands for the react. Let's take a question. Let's take a the decomposition reaction of ammonia is a zero order reaction. The decomposition reaction of ammonia is a zero order reaction. The decomposition reaction of ammonia is a zero order reaction. The decomposition reaction of ammonia is a zero order reaction. The decomposition reaction of what? Ammonia is a what? Calculate the amount of 0.800 mole per liter of ammonia. Calculate the amount of 0.800. Calculate the amount of 0.800 mole per liter of ammonia left after 300 seconds. Calculate the amount of 0.800 mole per liter of ammonia left after 300 seconds. Calculate the amount of 0.800 mole per liter of ammonia left after 300 seconds. If the rate constant for the reaction is 2.66 multiplied by 10 raised to power minus 3 mole per liter per. If the rate constant for the reaction is 2.66 multiplied by 10 raised to power minus 3 moles per liter per seconds. Class. They said the decomposition reaction of ammonia is a zero order reaction. The decomposition reaction of ammonia. So ammonia is our reactant. When it decomposes, it will give you N2 plus 3H2. So 2NH3 decomposes to give N2 plus 3H2. We are not bothered about the product. It's only the reactant. When solving with rate equation, we are not bothered about the product. Only the what? Only the reactant. Follow me. Class, the rate constant K is 2.66 multiplied by 10 raised to minus 3. If we are to now include this NH3 into this formula, this is the formula for zero order reaction. It will be NH3T, the concentration of NH3 at a particular time. What's the time? 300 seconds. After 300, concentration of ammonia after 300 seconds must be equal to initial concentration of ammonia at 0 seconds minus rate constant K times time T. What's time T? 300. But the question already gave us time as 300 seconds. After 300. Let's look at the question. Calculate the amount of 0.800 mole per liter of ammonia left. Amount of 0.800 mole per liter of ammonia left after 300 seconds. That means what is the concentration of ammonia after 300? Class. Why they were asking us the question? They already suddenly gave us the concentration of ammonia, which is 0.80. Because you calculate the amount of 0.800 mole per liter of ammonia left. So the initial concentration was 0.800. Please, can you talk to those children for me? Don't let them stop making noise. You on green. You on green. Let me just tell them that, yes. What's the video? So 0.800 minus K is 2.66 times 10 raised to power minus 3. T, 3. This is the first one. So calculate the amount of ammonia left after 300. But calculate the amount of 0.00, they're giving you the initial. After 300. That's all. We're all together. Are we all together? Yeah, I lost. But I didn't ask you not say anything. I was blocking you. Why not come to this side? Why do you sit in a place that will make you put you at disadvantage? you are still enjoying yourself. Come now, sit here, look at sit here. That place is free. Why not just change your position? This pause the video. Alright, follow me now. When you multiply this by this, what do you have? 0.798. Right? 2.66 times 10 raised to minus 3 times 300 should give you 0.79. Is that correct? What is 0.800 minus 0.798? 0.002? Yes. Moles per liter per. So this is the concentration of Na3 after 300. This is the concentration of NH3 after 300 seconds. Quickly write that down and we'll go to first order reaction. First order reaction. You see there's only one example we took. Also, there's only one example your textbook gave you. Is that why you should now relax? No. Go to your past, resting. Take more exams. If you don't still have past question, you want to get one, let me know. So if I want to get the past question, let me know so that we can produce for you and get it ready. This exam time now. It's not time to waste with textbook. Go straight to your exam questions. Go straight to your past exam questions. Please let us be fast. First order reaction. These are reactions in which first order reaction. These are reactions in which the rate of the reaction is directly proportional. These are reactions in which the rate of the reaction is directly proportional. These are reactions in which the rate of the reaction is directly proportional. Is directly proportional. These are reactions in which the rate of the reaction is what? Directly proportional to the concentration of the species in the rate law. These are reactions in which the rate of the reaction is directly proportional to the concentration of the species, to the concentration of the species in the rate law. Raised to the power of 1. Raised to the power of 1. These are reactions in which the rate of the reaction is directly proportional to the concentration of the species in the rate law. Raised to the power of 1. These are reactions in which the rate of the reaction is directly proportional to the what? Concentration of the species in the rate law. Raised to the power of what? 1. Class. If we have R is proportional to the concentration of A, the order here is 1 first order. That will say raised to the power of what? The constant constant, so R equals to K, concentration of A, raised to the power 1, which is A. Right? A raised to the power 1 is A, right? Let us make K subset of the. If you make K subset formula, we have K equals to R divided by A, divided by what? Class, the unit for R is mole per liter per seconds. This symbol here stands for concentration. So what is the unit for concentration? Mole per liter. Concentration does not have per seconds. Concentration is mole per. So that by the time mole per liter up here cancels mole per liter down, we are left with only per seconds. Meaning that the unit for the rate constant for a first order reaction is S, seconds raised per minus. If we are to recall when we did zero order reaction, we concluded that R equals to K. So therefore the unit for K is the unit for R, which is mole per liter per second. So that the unit for the rate constant changes depending on the kind of order of the reaction. Class, follow carefully before you write. You will be asked in the exam, what is the correct unit for this a rate constant for a zero order reaction? Mole per liter per second. But what is the correct unit for a rate constant for a first order reaction? Is per seconds. So listen to the question carefully. What is the correct unit for the rate constant for a zero order reaction? Mole per liter per second. But what is the correct unit for the rate constant for a first order reaction? Per second. When we get the second order reaction, to change again. So please take. Integrated rate equation for a first order reaction. Integrated integrated rate equation for a first order reaction. Integrated rate equation for a first order reaction. Class, integrated rate equation for a first order reaction, we have logarithm of AT equals to minus KT all over 2.303 plus log A naught. This is the integrated rate equation for a first order reaction. Of course, we already know, class. This integrated rate equation can change if the reactant, if the component of the reaction are gases. If the reactant is a gas, this can change to log pressure. Instead of concentration, we use pressure. Pressure of A at a particular time, T, equals to minus KT all over 2.303 plus log pressure of A at what, 0 seconds. Class, we only use the second one. We change concentration to pressure. Every other thing remains the same. When all components of the reaction are what, gases. When we are dealing with gas, if the reactant is a gas, and then with gas, you can use pressure instead of concentration. If you're dealing with gas, you can use what? Pressure instead of what? Concentration. If you're dealing with a gas, you can use pressure instead of concentration. Let's take a question now. The rate equation for the decomposition of N2O5. The rate equation for the decomposition of N2O5. The rate equation for the decomposition of N2O5 is giving us. The rate equation for the decomposition of N2O5 is giving us Rn2O5 equals to K concentration of N2O. The rate equation for the decomposition of N2O5 is giving us Rn2O5 equals to K bracket N2O5, which is a first order reaction. For class, if they are giving you a question, they will tell you the order so that you will know the formula too. Because formula for zero order is different from formula for first, also different from formula for second. So you see, which is a first order reaction? Which is a first order what? Reactions. Now calculate the concentration of 0.5 mole per liter. Calculate the concentration of 0.5 mole per liter of N2O5 left. Calculate the concentration of 0.5 mole per liter of N2O5 left after 400 seconds of decomposition. After 400 seconds of decomposition. Calculate the concentration of 0.5 mole per liter of N2O5 left after 400 seconds of what? Decomposition. Calculate the concentration of 0.5 mole per liter of N2O5 left after 400 seconds of what? Decomposition. If K equals 5.15 times 10 raised to the minus 3 per second. Class, note the unit of K even in this question, per second. The unit of K in the first order reaction is per second. I wish you could go back to when they gave us K in that example of zero order. Check the unit, see that it's mole per liter per. Note this changes, note this what? Because someone that might not understand, why are they changing it if we didn't know the reason why? But wondering why they gave one question, they gave unit of K. I thought K should have the same unit now. How come unit of K is zero order, unit of K in first order? Now you understand the reason why. Now class, This say it is a first order reaction, so if any help you know what to do. Class, you don't give you a question, I don't want to mention the order of the reaction. For someone like zero order reaction, they will easily tell you that in the following reaction, the rate of the reaction is independent of the concentration of the reactant. In the following reaction, the rate of the reaction is independent of the concentration of the what? Once they tell you that, what kind of reaction are you dealing with? But in a zero order reaction, the rate of the reaction is independent of the concern. Please take note. Now, let's solve. What do we have? We have K, we have time, 400 seconds. Calculate the concentration of 0.5 mole per liter. That 0.5 mole per liter must be the initial N2O5 initial 0.5 mole per. It's a calculate the concentration of 0.5 mole per liter after. So that is final. So we're looking for the concentration after, which is the final after 400. This is what we are looking. Now applying the formula, class. Are we going to use this or this? We use the first one, right? Yeah. Because if we were to use the second one, the question would have come in with pressure, right? They have been giving us initial pressure and say find the final. But they are talking in terms of concentration, so we're going to use the first. But it's where the question will come in. And given that the initial pressure is also and so ATM, find the pressure after 400 seconds. Are you following? Or the dimensional pressure, so we're going to stick on the first one. So we're going to say log N2O5. I'm making this formula. A is now, our A is N2O, T is 4. So this is log 80, but now our A is N2O, because A should be the reactant you're dealing with at that point in. So log N2O5, see what's my time? 4 on equals to minus K, what's my K? 5.15 times 10 raised to minus 3. Who is my T? 4 divided by 2 plus log A naught. Who is my A naught? N2O5 naught, right? 0. Plus log 0.5. Class, normally, after I get to this point, it's a mathematics problem, right? This is what you're looking for. Can you arrive at your final answer? For an exam, I can teach you the chemistry. If you're having issues solving logarithm at this level, then it's just a waste of time teaching you the chemistry because you still need the final answer. And in kind of exam you're writing, it's the final answer that matters. Everything we're doing here does not even lecture, it's subjective, so it's just that final thing you put there. You don't even want to know how you got it. So your second semester exams will not even take time because just check the passage 1 hour 30, 1 hour 30, 1 hour, 1 hour 30, 1 hour, 1 hour 30 minutes. Because it's just subjective now. So final answer, what are you doing? Final answer. It's just one paper, front and back. You start everybody one paper. 1 to 18, page 1. The next turn flip, 19 to 30. Just final answer. Check the passage, see that it's just one page, the exam. These are things that person will help you to do. You have to know how what am I expecting. That's how you use passion to your advantage. Okay, I know what I'm expecting. This is how the exam looks like for this one. This one is OBJ, like this is OBJ. The two P's are OB. The FSB now is OBJ. AEB used to be subjective, but last set, college students, AEB became OBJ. You check the past question sources. So let's say I have 70 objective questions. 70 objective. So let us challenge ourselves. Everybody give me the final answer because I don't think anything I'm doing after here and it's not chemistry, it's mathematics. We should have known. We didn't come in mathematics. So let everybody give me the final answer. Give me the final answer today. How do you find answer? Shift. So how do you solve this? Bring this log over to this side. First of all, before you bring the log, solve everything on the right hand. So class, it's not shouldn't be that difficult. This times this is multiplying, Abby. Then divided by get your answer. Plus find log 0.5 the value. Add it to whatever you got. You have one particular thing, right? Now, if that means bring log to this side, it becomes anti-log. Everything you have done here, the anti-log of it will give you your final. You might not be exactly 0.0, maybe 0.0637 or in that line, right? 639. 637? 5. In that line, this is 63. You don't know when I'm going there, I'm going. I'm in that part of being correct. Class, believe you me, by telling you to do this, I'm actually helping you. Because if I solve this, I have not changed anything for you. I'm not changing anything for you because you see, if the exam is still solve it by yourself. So it's better you won't face it now. So when you're facing the second time in the exam, you're really okay, they have made us do this before. They have made us do it before. Second order reaction, second order. Don't forget, take more questions. I'm not taking as much examples as I should be taking. It's your own job now to go and take more questions. If I was taking enough examples I should be taking, I should still be in the first chapter, I should still be in the first topic by now. If you take like 10 examples, this topic will not leave here. So it's your job to go and build on it, please. Yes. Unit of concentration is mole per liter, yes? Oh, you got this per seconds. No, this is not, we are not looking for rate constant now. The question is not ask us to find rate. It's not as if everybody in first order is now per second, so who is per second? The rate comes. This is concentration is still mole per liter. Thank you for bringing that out. Second order reaction. These are reactions. Second order reactions. These are reactions. Second order reaction. These are reactions. In which the rate of the reaction, second order reaction, these are reactions, in which the rate of the reaction is directly proportional. Directly what? Proportional. Second order reaction, these are reactions, in which the rate of the reaction is directly proportional. Second order reaction, these are reactions, in which the rate of the reaction is directly proportional. Is directly what? Proportional to the product of the concentration of the species. Is directly proportional to the product of the concentration of the species in a rate law. Is directly proportional to the product of the concentration of the species in a rate law. Is directly proportional to the product of the concentration of the species in a rate law. Is directly proportional to the product of the concentration of the species in a rate law. And the sum of the exponential function of the concentration of the species is equal to 2. And the sum of the exponential function of the concentration of the species is equal to 2. Plus, all those big grammar, what do they mean? The overall order of the reaction is what? 2. We know it already, right? Nothing as good as understanding what you are writing down. I'll come again. And the sum of the exponential function, and the sum of the what? Exponential function of the concentration of the species. And the sum of the exponential function of the concentration of the species is equal to what? 2. And the sum of the exponential function, altogether, of the concentration of the what? Species is equal to what? 2. So in the second order reaction, total order, overall order of the reaction is 2, right? Long and short of everything they are saying. Overall order of the reaction is what? 2. Now class, what will be the yes? I'll just mention the rate constant for the second order reaction. Class, R equals to K A raised to power 2. This must be the rate equation for a second order. If you ask an example, give an example of a rate equation for a second order reaction. This is what you should write. Give an expression showing an example of a what? Rate equation for a second order. Remember that I first taught rate equation before I started teaching order. 0, second, first and second, right? I first taught rate equation. Now, this is the rate equation for a second order reaction. Class, make K set of formula. I want to find the unit for rate constant K. When it was zero order reaction, what was the unit for K? Mole per liter per. When it was first order, what was the unit for K? Per second. Now, second order, let's derive the unit for K for second order. It could be asked in the exam. K is R all over A raised to 2, right? I'm making K set of the. I want to make K set of formula. So divide both sides by A square, right? Divide both sides by A. A square cancels A square. So that K is R all over A. K is R all over A square. Now what is the unit for R? Normal rate of reaction normally. No matter the other, rate of reaction is mole per liter per. This is concentration of A. What is the unit for concentration of mole per? for correction is squared, so mole per liter. So we have 1 mole per liter up. If it kills 1 mole per liter down, there will still be 1 more mole per. Do you agree? Mole per liter square means mole per liter is occurring. So if 1 mole per liter kills 1 mole per liter, they still under 1 mole per liter will survive, right? So what's left of the whole thing? We have S raised to minus 1 of all over mole per liter down, right? Can mole per liter come up? If mole per liter comes up, their sign will change. Mole now be mole raised to minus. Per liter now becomes just liter, right? Remember what happens in mathematics now? When someone changes position from down up, the sign will change, right? If it's positive, becomes negative. If it's negative, becomes. So mole was down, it wasn't carrying minus. It comes up and takes a minus sign. Liter was down, it had a minus. Comes up and no longer minus. Per second was raised already up before, so this is the correct unit. Per mole liter per second is the correct unit for rate constant for second order. Until you open your person, that's when you might realize what we're doing here. They ask these things in the exam. They ask in the what? Exam. Integrated into equation, we have 1 all over 80 equals to 1 all over A naught plus KT. Integrated rate equation for a second order reaction, 1 all over 80 equals to 1 all over A naught plus KT. Any other thing I must say? That's all. Now, one more thing, effect of temperature on reaction rates. You want to look at Arrhenius equation. Arrhenius. So right now, solve it. Effect of temperature on reaction rates. Effect of temperature on reaction rates. Effect of what? Temperature on reaction rates. Effect of temperature on reaction rates. Effect of temperature on reaction rates. Want to look at Arrhenius equation. Under that, write down Arrhenius equation. Arrhenius. After writing the effect of temperature on reaction rates, class. Interestingly, we already explained the effect of temperature on reaction rates. Remember, when I told you that increase in temperature increase collision, right? Collision frequency increases, right? And when the more the collisions occurring, the more chances for what the product will form. More effective collision can occur. Arrhenius reaction. Now, class. So we just go straight to the Arrhenius equation aspect. I already explained the effect of temperature on reaction rate. Arrhenius equation. Class, Arrhenius equation relates the rate of rate constant K to temperature. It's an equation that relates the rate constant K to what? Temperature. Class, rate constant K and temperature. This is the equation that relates rate constant K and temperature. You will be asked in the exam. Class, I don't think you will escape a question on this in the exam. This is one of the most consistent topics. It comes out every year. So, funny thing is, even if lecturer said he doesn't want to repeat this question, there are some things he cannot just for. As long as he's still going to set exam in that scheme of work, you cannot escape some things. Because whether you want to repeat question or not, as long as you are asking questions on what you thought, right? Yeah. And you have covered everything that he thought, you will still be good. You will still be what? So, Arrhenius equation comes out very, very well. When we say they don't repeat, I mean they might not repeat word for word, but that's not that they will not bring out what's in the scheme of work. So they will bring the Arrhenius equation, but they will not bring the exact question they brought on the equation last year. But if you can solve the one of last year, then this year is just changing of values, right? You will still get log K equals minus EA all over 2.303 RT plus log A. This is Arrhenius equation. Log K. Log what? K. What does K stand for? Rate constant. Rate equals to minus EA. EA is activation energy. I've explained what activation energy, right? When I said cutoff mark, remember? Yes. I intentionally used some keywords, some very striking words to make you remember some things. So they said this thing. So I said cutoff mark. It was very intentional. So these I say and do are very intentional to make you understand, to remember them. Activation energy is the energy that is required before a reaction can proceed from reactant to. If that energy cutoff mark is not met, the reaction will not proceed. So what the catalyst does is that it comes and reduces the activation energy. So class, activation energy, R is what? Gas constant. R is what? What gas constant are we using here? 8.314. You know we have two gas constants. We have 0.0821 when we're doing gas laws in inorganic chemistry in the first semester. But this one is 8.31. This is the inorganic chemistry. What am I even saying? Joules per mole per Kelvin. This is the inorganic, but you know what I mean? When we're doing gas laws, it was 0.0821 now. For class here, we're using 8.314 joules per mole per T is temperature. The temperature must be in Kelvin. You can see per Kelvin. So temperature must be in. So T here represents temperature. You'll be given. It is given in degrees Celsius convert to Kelvin. You know how to do that, right? A represents your Arrhenius factor. Arrhenius factor, also known as frequency factor. Arrhenius factor, also known as what? Arrhenius factor, also known as frequency. For class, you know what? This is not even the this Arrhenius equation has a modification, and it's that one that is actually usually asked. But you could be asked to write out express mathematical expression for Arrhenius equation. This is it for class. When you now have two reactions with their different rate constants and their different temperature, you can be asked to find the compare and use K1, K2. You understand? T1, T2. So let us have a situation whereby we have K2 and K1. Another formula will come up log, and this one usually has log K2 all over K1 equals to EA all over 2.303 R. Now open a bracket. One all over T1 minus 1 all over T2. Log K2 over K1 equals to EA all over 2.303 R 1 all over T1 minus 1 all over T. Please, in case you attended the first one and I give you a different thing, it's still the same thing if you find the LCM. It's the same. But I know if you find the LCM, you're going to have T1. T1, T2 is divided by T1 is T2. T1 is divided by T2. You're going to have T2 minus T1 all over T1, T2. This is why I gave you that, right? Yeah. And if you're checking your notes, I'm just saying something different. It's the same thing. I can teach something 3 times. I just teach in different ways. It's still the same thing I'm hitting at class. So this is initial rate constant, final rate constant. K1 initial rate. We know that K stands for rate constant. K stands for rate. So K1 is initial rate constant. K2 is final rate. EA is activation. R is gas. T2 final temperature. T1 initial temperature. Let us round up today's class with a question. Let's round up today's class with a question. What's the time? 2:51. Oh, so the day is still early. Oh, so 12? Your time is wrong. That means we still have time now. I thought this time has even gone. To 12. Wow. That means we have like 4 hours left. Now let's continue. What's that? You said that time is to 12, right? Well, let's ask the time. Let's ask the class. Take this question down. The rate constant for the first order decomposition of N2O5. The rate constant for the first order decomposition of N2O5 at 15 degrees Celsius. The rate constant for the first order decomposition of N2O5 at 15 degrees Celsius. The rate constant. The rate constant for the first order decomposition of N2O5. The rate constant for the first order what? Decomposition of what? N2O5 at 15 degrees Celsius. The rate constant for the first order decomposition of N2O5 at 15 degrees Celsius is the rate constant for the first order decomposition of N2O5 at 15 degrees Celsius is 6.90. Is 6.90 times 10 raised to the power minus 2 times 10 raised to the power minus 2 is 6.90 times 10 raised to the power minus 2 per seconds. Per seconds means because it's first order, right? Per seconds. When I say per second, what are you writing? S raised to the power minus 1, right? Hope you're not spelling it as per S raised to the power minus 1. if the activation energy of the reaction is 88.0 kilojoules per mole, if the activation energy of the reaction is 88.0 kilojoules per mole, if the activation energy of the reaction is 88.0 kilojoules per mole, if the activation energy of the reaction is what? 88.0 kilojoules per mole. Determine the value of K if the temperature is decreased to 5 degrees Celsius. Determine the value of K if the temperature is decreased to 5 degrees Celsius. Determine the value of K if the temperature is decreased to 5 degrees Celsius. Determine the value of K if the temperature is what? Decreased to 5 degrees Celsius. Class, let us look at this question critically. So the rate constant for the first order decomposition of N2O5, the rate constant for the first order decomposition of N2O5 at 15 degrees Celsius, T1, 15 degree, how do you change to Kelvin at 27? What do you have? 288, right? 288. The rate constant for the first order decomposition of N2O5 at 15 degrees Celsius is, so the rate constant is, so K1 is 6.90 multiplied by 10 raised per minus 2 per. If the activation energy of the reaction, EA, is 88.0 kilojoules per mole, find the value of K, that's K2, find the final K2. If temperature has now reduced, T2, so we don't know K2. If temperature has reduced to 5 degrees Celsius, you change the 5 degrees Celsius to Kelvin plus 278 Kelvin, right? So in all, we're looking for K2. They didn't give us R because it's supposed to know that R is gas constant. You should know it, 8.314. So I think we have everything we need. It's only K2 we need. If you look at this formula now, only K2 is missing everything that we have here. So to apply it, we should be good. Don't forget this aspect can place what? T2 minus T1 all over T1. We're looking for K2 class. So let us make K2 set of the. But this formula says log K2 over K. Class, we can make K2 set of the formula by remembering that when logarithm of two components dividing each other, K2 over K1 can be written as log. Log K2 over K1 is the same thing as log K2 minus log K1. Do you agree? Class, let me just remind you quickly. Look up. Log A all over B. Log A divided by, it is the same thing as log A on its own minus log B on its own. Log A times B. If it is log A times B, if it is multiplication, what will it be? Log A plus log B. So if multiplication is addition, if it is division, it will subtract. So log A all over B is log A minus log B. So log K2 all over K1 is log K2 minus log K. Why do we have to detach K1 and K2? Because they cannot be together. Why? K2 is unknown, K1 is known. We need to make K2 instead of the formula. Otherwise, detaching it. So someone has given you an Arrhenius equation. It's your person. If you don't know how to bring it out like this, you will not be able to use it. So log K2 over K1 is something like log K2 minus log K1. Now log K2 and K1 are not separate. We can now bring log K1 to this side of the equation. Because everybody on this side of the equation is known. So that the unknown side can be on the left hand side. K2 is what we are looking. Let only the unknown side be on the left hand. That's how we following. So I'm giving you a reason for everything I'm doing so you can already understand it. Why am I buttressing on this aspect? I'm sure that it will come out. They bring questions on this. Class. And this particular equation why is it important again is that they will bring two questions. Do you know how? This equation is similar in chapter 2, chemical equilibrium. This equation appears again. Just like instead of this animation, it changes to molar heat change. And this K2 and K1, they don't represent rate constant anymore, they represent equilibrium constant, K1 and equilibrium constant, K2. So this same equation, Arrhenius also helped us in chemical equilibrium. So question that is from at least two. One from chemical kinetics, the other one from chemical equilibrium. I will remind you when we get chapter 2 tomorrow. Tomorrow is chemical equilibrium. I'll remind you of this Arrhenius equation, whereby this EA will change to molar heat. But let's deal with this one. So we are able to separate K2 and K1. Now we're going to say minus K1, if it moves to this side, what does it become? Plus K. Minus K1 moves to this side, become plus log K1. Do you agree? So you now see that only the person we don't know is on the left hand. So log K2 is on the left hand side. So we're going to say, let's now start solving. Who is EA? 88 kilojoules. Class, thank God you remember. Kilojoules cannot be used immediately. It should be changed to joules, right? There's a prefix that is hidden here that if you don't forget yourself, there's no option to tell you that you're wrong. You just write whatever you got dash. So the exam is very dangerous. You don't even know that you are. If it's OBJ, sometimes you will not even see your nonsense answer in the option. You'll be forced to go back again. But this one now, you have to write it there like that. 88,000. Convert your kilojoules to joules. 88,000 joules. Please take note. Kilojoules to joules multiplied by 1,000. So we're going to have 88,000 divided by 2.303. These are 8.31. Who is T2? T2 is 278. Who is T1? 28. All over. Who is T1? 288. Who is T2? 278. T1, T2 means T1 times T plus log. Who is K1? 6.90. Why am I talking to myself? What is that? Have you gone? Am I the only one in this class? Sir. They have gone. Keep asking here. 6.90 times 10 raised to the minus. I thought you have gone. 6.90 times 10 raised to the minus. Class. This becomes a mathematical problem. And once it becomes a mathematical problem, it becomes your problem. No longer my. I'll just give you the final answer, it's just to find out the answer. Because if I keep assuming solving everything, and assuming that you know it in the exam, you will not test yourself. And the exam, that will be the first time you'll not be solving by yourself. Because I've always been solving the mathematical aspects. So people did not even know that they don't even know how to change log until I made you do it by yourself. See that log K2 over K1, let's be honest, some people did not know it, or they forgot it. Maybe they know you have forgotten that this you can change it though. So as I want to force to be solving, that's nothing that makes students don't do well. You get to the exam now, you're not shocked for the first time, but you have never been solving, I've been doing everything in class. So class, give me your final answer for K2, it's a mathematical problem. Let me tell you what you should get if you are correct. Your K2, if you are correct, should be 1.84 times 10 raised to the minus 2. Please bring this answer for me tomorrow in class because at this junction we are done for today. Class, if you know yourself that if you leave this class, you will not touch your book again. Finish it now. Because if I was to solve this, you will still be in class. Because I've said we are done now, you will not carry your bag and go like that. Without making sure that you finished this. Class, I've given you something to know if you are correct or wrong. This is not the first time we are using log to solve today. Let me just give you a hint. At the point, after doing everything on this right hand side, this K2 will make self formula again. Log will come to this side and become anti. So after doing everything you get on the right hand side, you will get the anti-log of everything. But log will move to this side and become anti-log. At least you need to do this times this, do this. Find the log of 6.90 times 10 raised to the minus 2. This is what I'm doing is helping you because if you are forced to solve it now, the exam will not be too difficult again. Are we together? Yes. So do it now. Solve it now. So please, if you are following us online, also attend this. You are not exempt from this. We want to make sure that you are well grounded in your mathematical aspects so that you are not surprised when you get to the exam. If you couldn't attend class today because you had lectures, some people said they had lectures, please join us tomorrow. We'll be having class tomorrow. What time is okay for tomorrow class? 2 p.m. You have lecture 12 to 2 p.m. 132, right? Can 132 what? It's done. It's done? Okay, let's start by 12 tomorrow then. So tomorrow, please join us. If you miss today's class, join us tomorrow by 12 p.m. We're going to a serious topic, chemical equilibrium. Join us. Thank you very much. Yes.